Okay, so this is a lecture on continuous beams or continuous beam columns, and we want to derive the relationship between the slope angle and the moments. So let's say that we have a simply supported beam with the end moments MB and MA. So we have the angle theta A and theta B. So we want to derive whether our moments applied at A and B, aka MA and MB. So we want to derive a relationship between the angles and end moments. Okay. We know that we have a governing equation looking like this: EI y prime 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 plus Py prime prime is equal to 0. And we know that the general solution for this problem is y of x is equal to a sine kx plus b cosine kx plus cx plus d. And we know that the double derivative of x is equal to minus ak squared sine kx minus bk squared cosine kx. Our boundary conditions, it's a simply supported beam, so we know that y at 0 is equal to 0 and y at L is equal to 0 as well. And we know that we have a moment at A and a moment at B, so EI y, this is equal to MA, and EI y prime prime at L, it's equal to MB. So if we use our first boundary condition, the geometric boundary condition at x equals 0, we get y of 0 is equal to a sine 0 plus b cosine 0 plus c times 0 plus d is equal to 0. That is equal to 0. Cosine 0 is equal to 1. This is equal to 0. And d is just d. So d becomes then minus b. Okay, we could use other boundary condition at 0. So y prime prime at 0, that is equal to ei minus b k squared cosine 0 minus ak squared sine 0. This should be equal to ma. From this we get minus bk squared is equal to ma over ei. So solving for b, we get that b is equal to minus ma over k squared ei. So we can look at the other moment boundary condition. So EI y prime prime at L, this is equal to EI minus B, which is MA over K squared EI times K squared cosine KL minus AK squared sine KL. This is equal to MB. From this, we can derive that MA over EI cosine KL minus AK squared sine KL. This is equal to MB over EI. We can solve this for A. So we get A is equal to 1 over K squared EI sine KL times MA cosine KL minus MB. We can now update our y of x. That's equal to 1 over P sine KL times MA cosine KL minus MB. This is times sine KX minus MA over P cosine KX plus CX plus MA over P. This is of course when P is equal to K squared EI. Now we can use our last boundary condition that y at L is equal to 0. This then becomes 1 over P sine KL times MA cosine KL minus MB times sine KL minus MA over P cosine KL CL plus MA over P. This is equal to 0. We can then solve for C. So C is equal to MA over PL cosine KL minus 1 over PL times MA cosine KL minus MB and minus MA over PL. And we can see that this ultimately becomes MB minus MA all over PL. Inserting all the constants into y of x, we get that y of x is equal to 1 over P sine KL times MA cosine KL minus MB all times sine KX minus MA over P cosine KX plus MB minus MA all over PL times X plus MA over P. Okay. If I multiply everything out, we get y of x is equal to, we get MA times cosine KL over P sine KL, all this times sine KX, minus MB P sine KL times sine KX, minus MA over P times cosine KX plus MB over PL times X minus MA over PL times X plus MA over P. Now we can factor out MA over P for those terms that have that one, and we can factor out MB over P for the terms that include those. Okay, so we get MA over P, then we have cosine KL over sine KL times sine KX minus cosine KX minus X over L plus 1 plus MB over P times X over L minus sine KX over sine KL. Okay. We can rewrite this a bit. Let's see that this becomes y of x is equal to MA over P times cosine KL over sine KL sine KX minus cosine KX plus L minus X over L plus this MB over P times X over L minus sine KX over sine KL. So this part I can write in a simpler way. So we have cosine KL over sine KL times sine KX minus cosine KX. This term I can rewrite in a much simpler way. So we need to remember that A sine to some angle theta plus b cosine to some other angle or the same angle theta, it's equal to r sine of theta plus some alpha, where r, that's equal to a squared plus b squared, and alpha is equal to the tangent inverse of b over a. So a in our case, that is cosine kl divided by sine kl, and b is equal to minus 1. So our r becomes square root of cosine squared kl over sine squared kl plus 1. This is equal to cosine squared kl plus sine squared kl all over sine squared kl. This is of course equal to 1 over sine squared kl. So r is then equal to 1 over sine kl. Alpha in this case is equal to the tangent inverse of minus 1 times sine kl over cosine kl. That is equal to tangent inverse of minus tangent to kl, and that is equal to, so the tangent inverse to tangent to the minus kl, that is just equal to minus kl. So this term cosine kl over sine kl times sine kx minus cosine kx, that is equal to 1 over sine kl times sine of kx minus kl. So this is equal to sine of k x minus l all over sine kl. Or we can say it's negative of sine of k times l minus x sine kl. So y of x then becomes ma over p times l minus x over l minus sine k times l minus x all over sine kl plus mb over p x over l minus sine kx over sine kl. If we now take the derivative of this function, we get y prime of x is equal to MA over P times minus 1 over L minus K cosine K times L minus X all over sine KL plus MB over P 1 over L minus K cosine KX all over sine KL. This is equal to MA over P times K cosine K times L minus X over sine KL minus 1 over L plus MB over P 1 over L minus 1 over L minus K cosine KX over sine KL. Okay. Now if I put in y prime at 0, we get MA over P K cosine KL all over sine KL minus 1 over L plus MB over P 1 over L minus K cosine KL over sine KL. This is equal to MA times K, factor out the K, and we get 1 over tangent KL minus 1 over KL plus factor out the K here as well. So we get 1 over KL minus 1 over sine KL. So we can use the fact that P is equal to K squared EI okay. Made a little mistake here. It's not KX. This should be K cosine K times 0. That, of course, is 1. That's why we get this 1 down there. So P is K squared EI. Get 1 over tangent KL minus 1 over KL plus MB K over K squared EI 1 over KL minus 1 over sine KL. If we let U equal to KL over 2 and also let K equal to then 2U over L, we get this is equal to MAL over 2 UEI times 1 over tangent 2U minus 1 over 2U plus MBL over 2U EI 1 over 2U minus 1 over sine 2U. This becomes MAL over 3EI times 3 over 2U 1 over tangent 2U minus 1 over 2U plus MB times L over 6EI times 3 over U 1 over 2U minus 1 over sine 2U. So if we let theta A is equal to minus y prime at 0, then we get that theta A is equal to MAL over 3EI times 3 over 2U 1 over 2U minus 1 over tangent to U plus MB times L 6EI times 3 over U 1 over sine 2U minus 1 over 2U. This we can write as theta A is equal to MAL over 3EI times sine of U plus MBL over 6EI times the function phi of U. We can do the same for y at L, y prime at L, and we get that theta B that is equal to MBL over 3EI times 3 over 2U 1 over 2U minus 1 over tangent to U plus MAL over 6EI times 3 over U times 1 over sine to U minus 1 over 2U. So theta B becomes MBL over 3EI times this psi of U plus MAL over 6EI times this phi of U. So this psi of U becomes, that is 3 over 2U 1 over 2U minus 1 over tangent to U, and this phi of U, it is 3 over U times 1 over sine to U minus 1 over 2U. And that is module 6.